This is SpaceTime Series 24, Episode 40, coming up on SpaceTime. Confirmation of how the universe evolved. The OSIRIS-REx spacecraft undertakes its final asteroid observation run. And Jupiter's great red spot still there and raging. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Astronomers have discovered that much of the universe's so-called missing normal matter has been hiding in plain sight in the cosmic web. The findings, reported in the journal Astronomy and Astrophysics, matches previous computer models of the evolution of the universe. The large-scale structure of the observable universe has a web-like appearance, with massive empty voids surrounded by thin filaments and connecting nodes made up of gas, stars, galaxies, galaxy clusters and superclusters. Our own galaxy, the Milky Way, together with all the neighbouring galaxies around us in the local group, are located on one of these thread-like filaments, right next to, and maybe even just inside, a giant void. When the universe exploded into existence 13.82 billion years ago in what today is commonly referred to as the Big Bang, matter expanded out from a single point in space-time, spreading out almost evenly in all directions. Almost evenly, but not completely so. In some places, matter was just a little bit more dense than in others. And these denser regions exerted slightly higher gravitational forces, drawing more and more gas and material from their surroundings. That's how the giant voids were created, with the increased concentration of gas eventually condensing into the filaments of galaxies, stars and planets which make up the universe today. But when astronomers did their calculations, they discovered that at least half of all the universe's so-called ordinary matter, technically what astronomers refer to as baryonic matter, remained hidden. Over recent years, there have been tantalizing clues, and we've discussed it both here on SpaceTime and on its predecessor Star Stuff, that this missing matter is spread out within the filaments between galaxies. Now, new evidence based on large-scale observations combining data from the Australian Square Kilometre Array Pathfinder radio telescope and the Earth-orbiting German Rosetta X-ray space telescope have confirmed it. The two telescopes' large fields of view allowed them to observe a relatively massive part of the sky in a single measurement and at very high resolution. They examined a system of 3 galaxy clusters known as Abell 339195, located some 700 million light-years away. The observations looked at not only the clusters and the numerous individual galaxies within them, but also at the gas filaments connecting these structures. Astronomers identified X-ray emissions emanating from gigantic gossamer-thin sheets of gas, at least 50 million light-years long, but possibly much larger, as that was the maximum extent of the field of view. One of the study's authors, Professor Ray Norris from the University of Western Sydney, says calculations suggest that more than half of all baryonic matter in the universe is contained in such filaments. It suggests that the widely accepted standard model for the evolution of the universe is correct. That model, called lambda cold dark matter, uses the combination of a mysterious invisible type of matter called dark matter and an equally mysterious force that appears to work opposite to gravity called dark energy to explain the way structures in the universe should appear. Norris says the observations reveal the striking richness of structure and activity in the merging cluster system.
So, our understanding of the universe is that after the Big Bang, all the hydrogen gas that was formed after the Big Bang collected into clumps. And these clumps pulled together by their own gravitational forces. And over time, it forms this web-like structure, which we call the cosmic web. So what we expect from these models is that all the galaxies we see should be strung along filaments and sheets with great voids in between. So that's what our theory tells us. That's based on our understanding of dark matter and dark energy and so on. And when we look at the galaxies, indeed we see these shapes, it looks like a cosmic web. We've never actually detected the gas in the filaments which we expect. So what we found in this new result that we've published is we've actually detected these hot gas filaments joining the galaxies. And so this is another step in confirming that our basic model with dark matter and dark energy is correct.
It also explains where all the missing baryonic matter is, because this has been one of the big puzzles, not just the missing dark matter that's very trendy to talk about, or what the dark matter even is, but the big head scratch has been, well, where's all the normal matter, or most of it? A lot of it's missing.
That's absolutely right. So when we count up all the matter we see in stars and galaxies, there's still not enough of it. We still expect to see more. And what we've discovered in this filament is that all this mass of hot gas strung out between the galaxies, which very nicely explains the missing matter.
And how is this research carried out?
Right now, there are these two big new instruments which are both surveying the sky. And one of them, eROSITA, which is built by the Germans, is looking at X-rays. And the other one, ASCAP, built by Australia, is looking in radio waves. So we're both doing a very similar thing, but very different wavelengths. And in this collaboration, we've come together because we realized we actually look at very similar things. And so collaboration is obvious. And so in this result, we've actually used both telescopes, eROSITA and ASCAP, to survey large areas of the sky and look around this cluster and see what we see. So eROSITA actually detected the bridge. They detected the hot gas. We didn't see it with ASCAP, and that's interesting. That tells you, because we expected to see it with ASCAP, and we expected to see all the electrons whipped up by turbulence in this gas, and we would see the radio emission from these electrons, and we don't. So that tells you that the electrons are not being whipped up by turbulence. It's quite smooth. And what we do see in the radio, we see galaxies along the filament, and those galaxies are falling down into the clusters. Clusters are where the filaments join each other, and the galaxies just appear to be falling down smoothly and not being buffeted by turbulence.
When we talk about something that's 700 million light years away, we think of that as being a long way away, but I guess on the cosmic scale of things, it's not.
That's right. Yeah. So we look at things further away. That's right. So, and of course, as we look further away, we go back in time, because if we look at something, let's say, 10 billion light years away, that means it's taken the light or radio waves from that object. It's taken it 10 billion years to travel from that object to us, to our telescopes. And so we're actually seeing it as it was 10 billion years ago when the light or radio was left it. So when we look out further and further in the universe, we're also looking back in time when you see the very early universe. And so it's really good for this sort of stuff, because we can see we can see the clusters like this one, we can see how they're joined. And we go further back in time by looking at objects further away, and we can see the proto-clusters, when the clusters are first forming, when the cosmic web is first pulling together. And so we can see all the stages of the formation of the cosmic web.
It's a bit like trying to see the forest for all the trees. Is it a difficult job to be able to place ourselves in the universe on that scale?
Well, you're right about the forest and the trees. I mean, one of the problems is that we've had these fantastic telescopes in the past which are able to see exquisite detail in these things. But what we really need to see these clusters is we need telescopes that will see large areas. And this is what both eROSITA and ASCAP do. They're really good at looking at large areas of sky. So our ASCAP radio telescope, it can see as deep into the universe as any other telescope. But its real magic is it can see large areas at once. And so we are seeing things that people have never seen before, just because they haven't been able to stand back. You know, we've been studying the trees, we're able to see the patterns in the forest as well.
With these new observations, does that put an end to MOND, modified Newton? Or shouldn't we go there?
Some of us would say that MOND was dead a long time ago, but...
This provides further support for lambda cold dark matter.
That's a really good question. So we've known for a while that models of dark matter have problems. So we know there's mass there that we don't see. We see stars going around galaxies, we see galaxies going around clusters, and it's as if there's a whole load of missing mass there, which we call dark matter. Now, MOND is an idea that maybe there's no dark matter. Maybe it's just that MOND stands for modified Newtonian dynamics. Maybe our laws of gravity are slightly wrong. And it's a good idea. But the trouble is MOND attacks problems piecemeal. It doesn't actually give you an alternative theory, and it doesn't predict stuff that we're seeing. So, for example, this discovery of the cosmic web, the filament we've now found, that's totally predicted by our idea of dark matter. This is not predicted by MOND. So I wouldn't say this is what kills MOND stone dead. I would say MOND has been comatose for a while. And the prognosis is not good.
That's Professor Ray Norris from the University of Western Sydney. And this is Space Time. I'm Stuart Gary. Still to come, NASA's OSIRIS-REx spacecraft undertakes its final flyby of the asteroid Bennu, and Jupiter's grey-red spot may be shrinking, but it's still raging. All that and more still to come on Space Time. NASA's OSIRIS-REx spacecraft has undertaken its final flyover of the half-kilometre-wide asteroid Bennu, passing just 3.7 kilometres above this alien world's rugged rock-strewn surface. The flight path took OSIRIS-REx directly over the sample collection site where the spacecraft touched down last year, giving mission managers a chance to see how the operation altered the asteroid's surface. The spacecraft's sampling head sunk almost half a metre in the asteroid's surface and simultaneously fired a pressurised charge of nitrogen gas. After collecting some 60 grams of regolith, the spacecraft fired its thrusters during the back-away burn, in the process disturbing a substantial amount of surface material. Because Bennu's gravity is so weak, these various forces had a dramatic effect on the sample site, disturbing and launching away many of the region's rocks and a lot of dust in the process. The final flyby of Bennu thereby provided scientists with an opportunity to learn how the spacecraft's contact with the Bennuvian surface altered the sample site and the region surrounding it. OSIRIS-REx imaged Bennu on its final flyby for 5.9 hours, just over the asteroid's full rotational period. Within this time frame, the spacecraft's Polycam imager obtained high-resolution images of Bennu's northern and southern hemispheres, as well as its equatorial region. Scientists will be able to compare these new images with the previous high-resolution imagery of the asteroid obtained during 2019. Most of the spacecraft's other science instruments were also on collecting data during this final flyover, including the MapCam imager, the thermal emission spectrometer, the visible and infrared spectrometer, and the laser altimeter. Exercising these instruments is also giving mission managers a chance to assess the current state of each science package aboard the spacecraft. That's important, as dust would have coated many of the instruments during the sample collection event. Understanding the health of the instruments is also part of NASA's evaluation process for a possible extended mission once the sample's delivered to Earth. OSIRIS-REx will remain in Bennu space until May 10th, at which point the mission will begin its return cruise phase, a 2-year journey taking it back to planet Earth. As it approaches the Earth, OSIRIS-REx will jettison its sample return capsule containing the rocks and dust collected from Bennu. The capsule will parachute down onto the Utah desert on September the 24th, 2023. Once recovered, it'll be transported to NASA's Johnson Space Flight Center in Houston, Texas, where samples will be carefully removed and then sorted for distribution to laboratories around the world for detailed analysis. The 2,110-kilogram OSIRIS-REx spacecraft was launched aboard an Atlas V rocket from the Cape Canaveral Air Force Station in Florida on September 8, 2016, on a 2 billion-kilometre, 7-year sample return mission to the near-Earth asteroid Bennu. Bennu is listed as a potentially hazardous object, with a 1 in 2,700 chance of impacting the Earth sometime between 2175 and 2199. An accurate assessment of Bennu's probability of Earth impact requires an accurate and detailed understanding of the asteroid's shape, its composition, and its rotational parameters in order to determine the magnitude and direction of what's known as the Yukovsky effect. The Yukovsky effect is caused by sunlight warming the dayside surface of a rotating body such as an asteroid. As the asteroid turns, the night side cools and releases this heat, which acts as a small degree of thrust, exerting a force which actually can be strong enough to change an asteroid's direction over time. Astronomers calculate that if Bennu were to impact the Earth, the expected kinetic energy associated with such a collision would be equivalent to 1,200 megatons of TNT. Bennu will pass within 750,000 kilometres of the Earth on September the 23rd, 2060. That close approach will cause a divergence in Bennu's next close approach to the Earth on September the 25th, 2135, which will be somewhere between 100,000 and 300,000 kilometres. Now, there's no chance of an Earth impact in 2135, but it will be close. However, that 2135 approach could position Bennu to pass through a 55-kilometre wide gravitational keyhole, which could then create an impact scenario at a future encounter. So, the more we know about Bennu, the better. This is SpaceTime. Still to come, Jupiter's Great Red Spot continues to shrink but is still raging. And later in the science report, Australian medical experts recommending people under 50 be given the Pfizer COVID-19 vaccine rather than the AstraZeneca jab. All that and much more still to come on SpaceTime. Over the last few decades, astronomers have noticed that Jupiter's most iconic feature, its Great Red Spot, which has raged across the surface of the solar system's largest planet for more than 300 years, has been slowly shrinking and fading. Observations by NASA's Hubble Space Telescope confirm that the rate at which the massive anticyclone is shrinking has slowed down in recent years, although it's still some 240 kilometres smaller now than what it was as recently as 2014. The Jovian Great Red Spot had been measured as far back as the late 1800s, at which time it was some 41,000 kilometres wide, big enough for planet Earth to fit inside it 3 times. But by the time NASA's twin Voyager spacecraft flew past the gas giant in 1979, the Great Red Spot had shrunk to about 23,300 kilometres across. And it's continued to shrink with time. A Hubble image taken in 1995 measured the spot at 21,000 kilometres wide, and by 2009 it had shrunk to just 18,000 kilometres across. Observations in 2012 revealed a noticeable increase in the rate at which the spot was shrinking by some 933 kilometres a year, and it was also changing shape from an oval to a circle. However, the most recent measurement showed the rate of shrinkage has slowed down somewhat, with the Great Red Spot now around 15,000 kilometres across and decidedly pale orange instead of red. Mind you, the storm's swirling winds still pack a punch, reaching more than 540 kilometres an hour around its periphery. Cyclones, including their regionally named counterparts, hurricanes and typhoons, usually spin around a centre of low atmospheric pressure. And a planet's rotation induces a Coriolis effect, which causes a cyclone to spin clockwise in the southern hemisphere and counterclockwise in the northern hemisphere. But the Great Red Spot is an anticyclone. They spin in the opposite direction because they're centred around an area of high atmospheric pressure. Over the past few years, astronomers have observed an interacting series of smaller vortices which are causing chunks of the Great Red Spot's clouds to flake off, further shrinking the storm in the process. Before 2019, it was only being hit by these smaller storms a couple of times a year. But more recently, it's being pummeled by as many as 24 a year. The Great Red Spot is still some 6 to 7 times as big as the smaller anticyclones that have been colliding with it. Mind you, to put all that in perspective, even these smaller storms are still some 10 times bigger than Earth's biggest hurricanes. Some are even bigger than the planet Mars. Now, a new study reported in the Journal of Geophysical Research Planets claims these interactions are only superficial, and the Great Red Spot's actually gaining power from these smaller storms at the expense of their rotational energy. New images of these storms, taken by NASA's Juno spacecraft in orbit around Jupiter, show that the smaller anticyclones pass through the high-speed peripheral ring of the Great Red Spot before circling around it. These smaller storms create chaos in an already turbulent and dynamic situation, temporarily changing the Great Red Spot's 90-day oscillation in longitude and tearing streams of red clouds from the main oval. But scientists say this is only affecting a few kilometres at the surface and doesn't have any significant impact on the overall 200-kilometre depth of the Great Red Spot as a whole. Scientists still aren't sure what's causing the Great Red Spot to shrink, or for that matter, how it formed in the first place. But they believe that these smaller anticyclones may actually be maintaining the Great Red Tempest, at least for now. And time now to take a brief look at some of the other stories making news in science this week with a science report. Australian medical authorities are recommending that people under the age of 50 be given the Pfizer COVID-19 vaccine rather than the AstraZeneca jab because of concerns of patients getting a rare type of potentially fatal blood clot. The move is based on recommendations by the Australian Technical Advisory Group on Immunisation and Australia's Therapeutic Goods Administration. It comes in the wake of research by the European Medicines Agency in Amsterdam, which found a clear association between the AstraZeneca viral vector vaccine and a rare type of brain blood clot associated with lower platelet counts known as cerebral venous sinus thrombosis. The agency found a 1 in 250,000 chance of people who take the AstraZeneca jab will wind up suffering from the clotting, with at least 79 known instances from a first dose, resulting in 19 deaths, including 3 under the age of 30. In Australia, a 44-year-old Melbourne man was hospitalised with the thrombosis following an AstraZeneca inoculation. Around the world, a growing number of nations are now either banning or restricting use of the AstraZeneca vaccine in the wake of the latest findings. The key side effects to look out for include headaches, blurred vision, breathing problems, chest pain, leg swelling, abdominal pain, skin bruising, and spots beyond the injection site. Almost 3 million people have now died from the COVID-19 virus, and another 135 million have been infected since the deadly disease first emerged from Wuhan, China, and spread around the world. The most comprehensive study ever undertaken has found autism to be far more common than previously thought. The findings, reported in the Journal of the American Medical Association, show that 1 in 57 children in the United Kingdom, that's 1.76%, were on the autistic spectrum. That's significantly higher than the 1% previously estimated. The study is based on data on over 7 million kids from the UK's National Pupil Database. Researchers found boys showed a prevalence of autism of 2.8% and girls showed a prevalence of 0.65%. Resulting in a boy-to-girl autistic ratio of 4.3 to 1. Prevalence was highest among pupils of black ethnicity at 2.1% and lowest in Roma populations at 0.85%. Well, it seems nature's strongest known material now has some stiff man-made competition. Researchers have produced artificial hexagonal diamonds which are harder than common cubic diamonds found in nature and often used in jewellery. Named for their 6-sided crystalline structure, hexagonal diamonds have been found naturally at some meteorite impact sites, and others had been made briefly in labs, but they were either too small or too short in existence to be measured. Now, a report in the journal Physical Review B claims scientists have finally produced hexagonal diamonds large enough to measure for their stiffness using shock compression experiments. They found them to be significantly stiffer and stronger than regular gem diamonds. The authors say hexagonal diamonds could be a superior alternative for machining, drilling, or any type of application where a cubic diamond is normally used. Well, just in time for Passover and Easter comes a new survey looking at Australian religious and spiritual beliefs. The survey of 1,000 people by McCriddle Research for the Centre of Public Christianity and published on the ABC found that around 2/3 of people either believe in or were at least unwilling to dismiss the existence of ghosts, angels, miracles, a higher power, that people have souls, or that there's life after death. Researchers found that younger people and females were more likely to believe in or at least be open to the idea, while males and older people tended to be more sceptical. The survey also found that some 43% of people either believe in the resurrection or think that it was at least possible. Around 41% hedged their bets, saying they either didn't know or think it's unlikely, and just under 16% say it didn't happen. In one of those iconic twists of the fickle finger of fate, one of the world's leading coronavirus skeptics has died, and we think it was from coronavirus. As Tim Mendham from Australian Skeptics reports, the president of Tanzania, who had denied the impact of COVID-19 and claimed his country's been saved from the disease by prayer, has suddenly died aged 61.
He was sick for a few weeks. It was described as the heart complication, that's a quote. But there's not a lot of real details or anything like that, but he was pretty sudden because he was 61. So, not particularly aged. And some people are suggesting that he might have died of coronavirus.
as he was a strong anti-coronavirus conspiracy theorist who reckoned that people of Tanzania were protected from COVID by having gone through 3 days of prayer in last year, and also that COVID can be treated with steam. In other words, put a blanket over your head and breathing up steam from a bowl of hot water or something like that. Anyway, but so when he died, everyone started thinking, oh, what did he die of? And that's your Schadenfreude, whether you're thinking, did he die of coronavirus, and isn't that ironic? But actually, at the time, a lot of people were spreading rumours about why he might have died, and unfortunately, the police started arresting people for spreading rumours. So you're not even allowed to suggest that it might have been COVID. The issue was that no one knew how widespread was COVID in Tanzania because they just didn't bother taking numbers or doing tests.
Yeah, they'd stopped taking numbers back in May last year, hadn't they?
That's right, yeah. So, when they say we've conquered this disease and we don't take any cases, that's easy enough to say when you don't test anybody. And so anyone who dies of it, you just sort of pass it off as something else. So they had no idea what sort of percentage of people are testing positive, how many people are dying at all. So it's, unfortunately, if it wasn't so serious, it'd be a bit of a joke. But unfortunately, it is pretty serious. And the local health people were actually saying, wear masks, be socially distant. But the president, John Magufuli, was basically contradicting them the whole time. So the health people there weren't having a great experience, a bit like what was happening in Brazil. They get the president who's suggesting that, it's all a conspiracy, it's all phony. And the health people there are struggling mightily to try and solve things. And Brazil is, of course, now going through a terrible time.
That's Tim Mendham from Australian Skeptics. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more SpaceTime, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary. And SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.